Okay. Am I audible? Can someone confirm? Okay. Okay. Thank you. So today is the 10th interaction session on NPTEL PMRF of design of steel structure. So today, first we will discuss about the flexural members, more specifically about beams, where we will discuss different kind of beams, then their mode of failures, different IS specifications for designing them. Then we will move to laterally supported beam, where we will learn how to calculate the design strength of the laterally supported beams and how to design them. Then we will spend some time on laterally unsupported beams. Okay. Lastly, we will solve the previous year examples. So beams, okay, more specifically the flexural members, right? Flexural members, whom we call the flexural members, the members which are, undergoes deflection due to application of loading. So let's start with the very beginning. Say for example, we have a beam. So for now, I'm taking a rectangular section of beam. Now, say for example, we have a beam. Now this is supported like let's put some support condition here. Say for example, this is simply supported beam. Okay. Now first let's try to understand about the axes. So if I consider the axis about or along its length, we have one axis and we have another two axes perpendicular to the axis which I with respect to the length. So first thing, for a beam, we have three dimensions like the length, the longer dimension generally we call the depth or height of the beam, and the width of the beam. So the axis with respect to the length of the beam, we call them the longitudinal axis. And the two other axes we call the transverse axis. So the beams or the flexural member generally subjected to the transverse loading. That means the load may come from the transverse direction. The load might come from this direction, positive this direction, or negative this direction, or may come from this direction also. Okay. So what happened if this beam is subjected to, one directional, that transverse loading? That means the beam will undergo bending, right? Now the thing is, if I fix one axis with respect to the application of load, then what will happen? Say for example, if the load is applied along, say, let me clear it. Then, say for example, load is applying x and y. This axis is z. So load is applying, uh, you know, from positive x y axis. Now this direction is the transverse direction. Now the thing is, other direction, this positive z or negative z axis, if I call this direction, will become the lateral direction of the beam. So the beam may be supported on the lateral direction or may not be supported with respect to the lateral direction. So two cases may occur. So we will go into it later. So till now, what we understand about the beams, that they are the flexural members, they are subjected to transverse loading, and due to this transverse loading, what will happen, at the cross section of the beam, different shear forces and bending moment will generate. Okay. Now we need to look for the shear force and bending moment which is generated in the beam. Then we need to design the beam accordingly. So before going to the design part, we need to know about the mode of failures of the beams. So what should be the primary mode of failure of the beams? Okay. So what I have discussed here, that like flexural member, we commonly call it beam in a steel building. Then they are subjected to transverse loading. Okay. The transverse load will produce the shear force and bending moment and all the things. You can read them out. Now, okay. So what I am saying, that what should be the mode of failure? Okay, before going to be there, or before discussing the mode of failure, let's discuss about some different kind of beams. Like in a steel building, joist. What is joist? A closely spaced supporting floor or roofs. The beams in a building which support the floors or roof. Like here you can see these are the joists in a steel building, above which the floor or slab will be casted or will be erected, or you know uh, situated. Now what is the girder? Girder is a large beam, that beam who, on which the joists are supported. Okay, and then purlin in a roof truss, that beam we call a purlin. Like we can see here on the next diagram. Here the purlins, we can see that longitudinal beams over that truss, purlins. Okay, now one more thing we have in a truss, like a rafter, the principal rafter one, that is also we need to design them as per beam. Lintel, we have lintel like in a masonry wall, to support the load from masonry wall, and for opening different kind of opening in masonry wall we need the beam, then we call the lintel. Okay, so they are the different kind of beams. Like many more kind of beams can be there. So firstly, to design the beams we need to know about the failure criteria. What should be the primary mode of failure? So what kind of load is coming on the beams? They are transverse in nature. That means bending moment and shear force will occur. So if the bending will occur, then firstly we need to look for the bending failure. Like if some load is coming, this is transverse loading, so the bending will occur. So we need to check or ensure that whatever beam we are going to design, or whatever section we are going to select for the particular beam, that section can withstand the bending stresses, or the stresses due to the bending moment, that can withstand. Now second thing, so due to that transverse loading, first bending moment will occur, and due to bending moment, what thing? Bending will occur, so we need to look for the bending stresses. Then one more thing is occurring due to that bending moment, that is the deflection, excessive deflection. So we need to look for the excessive deflection also, otherwise the serviceability condition will be hampered. Now due to that transverse loading, one more thing is occurring at the cross section of the beam, that is shear force is generating. Now due to that shear force, different kind of shear stresses will produce in the beam. Generally the web portion will take care of the shear. So while we will design the beam, we need to take care of the shear force also. If we can summarize this mode of failures, or primary mode of failures, they are generally occurring due to the application of the transverse load. So first thing, due to the application of transverse load, two phenomena is occurring. One, bending moment and shear force is generated. Due to bending moment, the beam will undergo bending, so we need to check for deflection, and we need to check for bending stresses, and also we need to look for the shear, that the shear force which is developed within that cross section of the beam, that our cross sectional area, the selected cross sectional area, should be able to take care of the induced shear stress or that force. So primarily we need to look for three kind of mode of failure. Now if we further categorize these things, then say for example, for a I beam or I section, what will be the mode of failures? So first thing, we need to check against the excessive bending, right? The bending moment, due to bending moment. Now one more phenomena can occur in the beams, particularly for the long beams, that we call lateral torsional buckling. Like for a long beam, what happened if the beam is not supported on the lateral direction? What will happen when some load is applying, when the some transverse load is applying? What will happen? Some twisting moment will generate, and that lateral torsional buckling thing can occur during the loading condition. Like here you can see the lateral torsional buckling for a long beam will occur. So how we can avoid this kind of lateral torsional buckling? So we need to specify some lanes and some more precautions we need to take, which we will discuss on the subsequent slides. Now, first thing, that overall failure can occur, like overall bending or the lateral torsional buckling. Two things. Now, locally the elements can fail, like the local buckling of flange can occur. Local buckling over there should not be overall buckling, but the flange may deflect or buckle. So there may be chance of local buckling of the flange, as well as different kind of local buckling, like the wave portion. The crippling of wave can occur, or buckling of wave can occur. So in general, if we look for different kind of mode of failures, firstly we need to look for the overall bending. Secondly, we need to look for the lateral torsional buckling. Thirdly, we need to look for different kind of local buckling failure. Like here you can see the flange portion has buckle, the local buckling failure occur. Or here we can see the wave portion, that wave portion got buckled. So three mode of failures or three stages we need to look for: overall bending, overall torsional buckling, and then local buckling of the wave portion and local buckling of the flange portion. Okay, now why I am discussing with respect to that I section. Generally for beams, what happened, we select or we choose the I section over different kind of sections, like let me go to that slide, like channel sections or angle sections. Why we don't prefer, like here generally we select the beam section as a, or I section, or hot rolled I sections as a beam sections, because it has certain advantages over other sections. Like angle section and T sections are weak in bending, but what we have just seen, that to design a beam properly, we need to look for the, or we need to ensure that it will not fail in bending, because the due to the transverse loading, bending moment will occur. Like channel sections we can only use for the light loads, otherwise there is a tendency of that that overall torsional buckling or local buckling failure things. So one more thing, that I and channel sections, for the calculation purpose, it is difficult to calculate that the different kind of portions, like how to calculate the or what should be the moment of inertia for these sections, and also different kind of buckling characteristics for them. These sections are little complicated to calculate. But for a I section, if you consider the I section, what will happen, we need to consider the bending stress. So we, from pure bending, we know how can calculate the bending stress. Sigma is equals to m by I into y, and the moment of inertia we can easily calculate, like bd cube by 12. So generally, for the few reasons, we prefer the I sections as a beam section over angle T or channel sections. Now let's move to the main part, like what should be the design criteria for beams. So we have seen that due to that transverse loading, beams are subjected to bending moment and shear force, and we have seen that there can be the mode of failure due to bending, due to deflection, and due to shear. And then we have categorized that, okay, firstly we need to look for the overall mode of failures, then locally what should be the mode of failure. So first thing, let's go with that deflection criteria. Deflection, we all know about the deflection, right? So if I say for example, we have a cantilever beam and subjected to some loading. Okay, this beam has length L, and say for example we have the load W kilonewton per meter, and that beam has modulus of elasticity E and the moment of inertia I. So we can easily calculate what should be the maximum deflection due to that load, right? That means, so for example, we have different kind of load arrangement, and for them we can calculate the different maximum value of deflection. For it, say for example, for this case of cantilever beam, what should be the maximum deflection? Delta max will be WLQ by ATI. Now look at this. That means the maximum deflection will depend upon the length, the intensity of load, modulus of elasticity, and moment of inertia both. So in general, we can simplify this deflection, maximum deflection thing like some constant into WL cube by EI, or we can easily calculate using different methods are there. We have already learned in structural analysis. So the main thing is, due to that lateral load, how much maximum deflection is occurring, delta max is occurring, and what should be the permissible limit for this condition. We need to ensure these conditions. So delta max, due to that application of load, we can calculate, and different values are given, like here for simply supported case, the value of k, here k, WL cube by EI. So the k value will be 584 for different kind of cases that are there. You can go through it. So the main point is, from there we can calculate the delta max due to, what is the delta max? Due to the application of that transverse loading. Now what should be the deflection limit? The deflection limits for different element with respect to different supporting condition is given in table number 6 of IS 800 2007. Here the allowable deflection limits are given. That means delta allowable are given. So obviously, to make our design safe, that delta max should be less than or equals to delta allowable, right? So if that condition satisfied, then we can say that okay, the beam which we are designing or we are going to design, that will be safe against your deflection. Now the deflection is okay. Now what should be the next thing? The lateral torsional buckling. So for the lateral torsional buckling, first thing we need to know what should be the effective length for lateral torsional buckling. So what should be the effective length? So we need to ensure that for our design, we should take, or we need to maintain some effective lengths. Like here, table number 15 will give you the complete details about the effective length for different cases. Like if that beam is free to rotate in plane, then the effective length should be L. If partially free to rotate in plane at the bearings, then 0.85 L. And subsequently, for the different kind of situations, we can take, and different kind of loading conditions also, we can take the values, or we can get the values from table number 15. Okay, when we will design one beam, or when we will calculate the design stresses like bending stresses and all these things, we will revisit this table again, and how to take the values from here and how to use them, we will see. So first thing, the deflection thing, okay, we can avoid by ensuring that maximum deflection should be less than equals to the allowable deflection, whatever is specified in Indian standard. And second thing is, okay, for the lateral torsional buckling, we need to consider some effective length for different kind of condition, and this effective length we can get it from table number 15. Now the main part we haven't discussed about, the main part, that is what happened, or what will we should do about the bending. So for the bending, what happened? Then now we need to categorize the beams into two parts, like laterally supported and laterally unsupported. So at the very beginning, I have said that talk about the lateral direction. Like if along this length, this is the longitudinal direction, and this too. So this is that is your longitudinal axis. This is your transverse axis. That means the beam is supposed to subjected the load from this side. So this axis here, so for example, this is X, this is Y, and this is Z. So positive Z and negative Z axis, along these axes, that will be the transverse direction of the beam. Or sorry, that Y direction is the transverse direction if the load is applying from this direction, and positive Z and negative Z is the lateral direction. Now, if a beam is supported on that lateral direction, that means, okay, I am ensuring that the lateral buckling thing will not occur. So for these cases, what should be the design bending stress? So for the laterally supported beam, so what are the laterally supported beams? The beams which are supported on the lateral directions. It can be supported on the supports and the mid span also. Now, how we can support them? Using some intermediate bracings, or different kind of sections which will be required to resist that lateral torsional buckling thing. So our code IS 800 2007 clause 8.2.1 gives the complete details about laterally supported beams. Here you can see a beam may be assumed to be adequately supported at the support provided the compression flange has full lateral restraint and the nominal torsional resistance at the support. Okay, that means that clause dictates that the how you can support the beam, or when you can say the one beam is laterally supported or not. That means simply on the lateral direction some supports are provided. That means indirectly that lateral torsional buckling thing will minimize. Now the thing is, for the lateral torsional buckling thing, how we can calculate the bending and shear property? Still now we don't know about the bending and shear properties. We have seen that due to deflection, what we need to do? Due to lateral torsional buckling, we can provide the lateral support and the effective lengths we have seen. Now what should be the design bending stress for the laterally supported? Okay, so bending strength of these beams are actually a function of your design shear, or or we can say it's a function of shear. Now clause 8.2.1 says two things. If first check if your beam is subjected to low shear or high shear. So we need to check two conditions before going to calculate the design bending stress. First thing, we need to check is my beam is subjected to low shear or high shear. So how we can you know identify the beam is in low shear or high shear? So clause 8.2.1.2 that says when the factor design shear force does not exceed 0.6 times of VD. That means what is that? That is the factor design shear force. And how we can calculate it? From the transverse loading and the position of loading, so on. That if this is less than 0.6 times of VD. VD, what is that VD? That is the design shear strength of the cross section, whatever we have selected. So how we can calculate the VD, we will see in a minute. So if this case happens, if this situation happen, that your beam, the shear, whatever the factored shear, that is less than 0.6 time of the design shear strength of the cross section, then the design bending strength MD, here you can see the design bending stress can be calculated as beta B ZP Fy by gamma m naught. Now what is that beta B? That is a factor which deals with the sectional properties, like is the section is plastic, is the section is semi compact, or different kind of things. So that sectional properties we will look into it in a minute. So that beta B, if we consider the section is plastic section, then the value of beta B is what? Simply 1. If semi compact section, then the value of beta B can be calculated as ZE, that means the elastic sectional modulus divided by ZP, the plastic sectional modulus. Okay. Now, so for the low shear case, and how we can check the low shear case? That means if the design uh, factored shear force, we need to calculate the first factored shear force which is generated on that, and what is the design shear strength, how we can calculate the design shear strength, we will look in a minute. So if this condition arises, we can calculate the design bending strength for the laterally supported beams as beta B ZP Fy by gamma m. So beta B is a factor. If the section is a plastic section, then 1. If other section, we can calculate it subsequently. What is the value of ZP? ZP is nothing but the plastic sectional modulus Fy. This is the yield strength, and gamma m naught. Now these values should be less than equals to 1.2 times JDFy by gamma m naught for simply supported beams, and for cantilever beams we need to check it for 1.5 JDFy by gamma m naught. Now why these two checks are needed? Because of here the code says to avoid the irreversible deformation under serviceable loads. Okay, there can be that load reversible thing can occur. So to ensure the serviceability condition, we need to check that okay, whatever the design bending strength coming for this laterally unsupported beam, for simply supported and for cantilever beams, they should be well within these two checks. Like for simply supported beams, we need to check for 1.2 JDFy by gamma m naught, and for cantilever beams this. That means eventually the design bending stress MD will become minimum of these two if we are going for simply supported beams, and minimum of this and this for cantilever beams. Okay, so by this way we can calculate the design bending strength of a laterally supported beams. Now if here what I said, that how we can quantify or find out which kind of section is this. Is it a it is a plastic section, is it a compact section or semi compact section? So here table 2 of IS 800 will give you the details about that sections. Like if we need to look for is the section is plastic or not, then we need to check B by TF ratio. If this ratio is well within that 9.4 epsilon, and what is that epsilon? Epsilon is nothing but under root of 250 by Fy. So if the yield strength of steel, whatever you are using, if the yield strength is 250, then Ji is simply become 1. So by this way, or from this table, we can identify whatever section we have selected, is the section is plastic section, compact section or semi compact section, and as per this we need to find out the different bending strengths. So first case for the low shear. Now if the design or factored shear force is more than 0.6 time of the design shear capacity, then for these cases the clause 8.2.1.3 8.2.1.3 here the clause says, for these cases the design bending strength can be calculated for two cases. Like if we have plastic and semi compact section, then the design bending stress can be calculated as MD minus beta MD minus MFD, and which should be less than equals to 1.2 JDFy by gamma m naught. Now if we have the semi compact section, then we can calculate the value of design bending stress like JDFy by gamma m naught. Now here what is that beta value? That beta value we can calculate like 2V by VD minus 1. What is that V? V is nothing but the factored shear force which is generated. What is VD? That is the design shear capacity or design shear strength, and so on. Now here one more factor like MFD. What is that? The plastic design strength for the area of cross section. So how we can calculate the value of MFD? It is nothing but if we have the rolled section, we can calculate H square TW by 4 Fy. What is that H? That is nothing but the overall depth of that rolled section. And for the built up sections, we can calculate like D square T by 4 into Fy. And why D is the effective depth for this section. So for high shear and for low shear, we can calculate the design bending strength for cases. Now, what I said, how we can calculate the shear. So we need to ensure the shear also, because due to the transverse loading, mainly the bending moment and shear forces will occur. So how we can calculate the design shear? So clause 8.4 of IS 800 will give the details about the design shear strength, and how the value of design stress strength, how we can calculate is that VD value is nothing but Vn, the nominal shear capacity, divided by gamma m naught, factor of safety against shear failure. The value is 1.1. Now what is the value of gamma n? Gamma n value is provided here. That means simply we can write it down, AV FYW divided by root 3 into gamma m naught. So here, what is that AV? So I will come into later. What is that FYW? That is nothing but the yield strength of the wave. And what is that AV? What is that AV? AV is nothing but the shear area. Now the shear area will be different for different kind of sections. Like the details of the shear area are also given in this clause 8.4.1.1, where that, like for I and channel section, what will be the shear area for hot rolled section? That will be nothing but H into TW. Why that TW? Wave portion we are considering, because in a beam that wave portion generally will take care of the shear. Because think about the shear distribution. We have the shear, the parabolic distribution of shear forces or shear stresses. So at the mid portion, the shear stresses will be maximum. The horizontal shear stress, remember that from your strength of material or solid mechanics class. So mainly the wave portion will take care the shear, and the flange portion will take care the bending moment. Okay, so here we can, from this clause, we can calculate the value of AV. What is that AV? AV is nothing but the shear area. Now, if we know the AV value, we can calculate the VD value. Okay. Now, if we can calculate the VD value, we can easily check the beam, whichever we are going to design, is subjected to high shear or low shear. Okay. And subsequently, we can find out the design bending strength for the laterally supported beams. Okay. Clear? Now, say we will talk about now that local failures. Here, till now, what we have done with the design process, like we have ensured three things. One thing, we have ensured the deflection. Okay. Overall deflection. Now we have ensured also that lateral torsional buckling thing, by providing that lateral stiffeners and some, maintaining some effective lengths. Then, okay, no problem. I will upload the video. Okay, no issue. If you have any, unseen later. Okay, no problem. No problem. I will upload the video on that channel. Okay. So what I was saying, yeah. So we have, uh, discuss about the overall things. Now we haven't discussed about the local, failures. So how we can deal with the local failures. So first thing, the web, that web portion can buckle, right? The web portion can buckle. So how we can, uh, reduce the tendency of wave buckling? So first thing, try to understand or visualize that the wave will act like a column. Okay, wave will act like a column. That means the failure criteria will govern by yielding. Now, generally they are thin, so there is a chance of buckling. Okay, now the thing is, for this wave buckling thing, we need to consider, first thing, we need to consider some, you know, effective depth for considering the portion. So what should be the effective depth? If the, conditions are lateral deflection and rotation, restrain against lateral deflection and rotation, like stiffeners are provided along this side and along that side also, opposite side of this face. So if that case is there, then the effective depth for that wave buckling thing will be nothing but d1 by 2. Why d1 is the, depth of the wave portion. Now, subsequently, for different kind of cases, like restraints against lateral deflection but not against rotation, like the twisting thing can occur at some places of the length, or along the length. then we need to consider the effective depth as a 2/3 of d1. D1 is nothing but the depth of the wave, and restrain against rotation but not against lateral deflection, d1. And different kind of cases will occur as per the design specifications of your problem. Now, wave buckling. Okay, so how to calculate the wave buckling strength? What should be the wave buckling strength? So the wave buckling strength is nothing but if dw is equals to area into the load. So wave portion, what I said, look at the wave portion. This portion, the wave portion will act as a column. That means, like in a column, what we have seen, that PED, design strength of the compressive strength of the column. What was that? That was nothing but AC, area of the column or compression area, multiplied by FCD, design compressive strength. Similarly, for the wave buckling strength, the FWB, that means the wave buckling strength should be B into TW. What is that B into TW? That is nothing but area of which we need to consider while calculating the wave buckling strength. Now, B, that B is differ in different condition. I will be here in a minute how we can calculate the B. Like B is calculated like B plus 2N1, where that B is nothing but the bearing length. Like if I draw a beam here, say for example, this is the beam. Say let me draw the beam, then I can so for example, we have a beam here. So one second. Okay, so let's say we have a beam here. Like what is that bearing length, all these things I will discuss now. Now if I say this is my beam and this is the neutral axis. Okay, now if a concentrated load is applied on it, so some bearing should be provided here. That means we are not directly applying the load on that area due to to avoid the stress concentration on that particular point. Okay, now what is, if we apply the load here, what will happen? The load will disperse generally in a 45-degree angle. Okay, now what is that B? B is nothing but the length of this portion B. At the if we are looking for B at the or under the load here, that will happen. And subsequently at the supports there is also the bearing is provided. That means for the support also we need to consider that B value. So for the for under that load or under that loading condition, the B value will be nothing but the bearing length. What is the bearing length? This is nothing but the bearing length, how much bearing I am providing, B, plus 2N. If we consider 45-degree load dispersion, so N, what is that N or N1? That is nothing but the distance from the top to neutral layer. So for this portion, B will be equals to nothing but capital B will be nothing but B plus 2N1. Now for the support portion, the B will become this portion or B1. Let it denoted by B1. So B1 will be nothing but N portion. B1 will be equals to B plus N, because we have two B1s from this side and from this side. If we check that one side of support, then eventually the other side of support against that wave buckling strength will be safe. So for to calculate that B, we need to know the bearing length. So the bearing lengths are generally provided, like okay, that much of bearing is provided here and that much of bearing is provided here. And if the bearing length is provided and if we know the overall depth of some section, then we can calculate the value of N1 also. N1 will be nothing but the depth divided by 2, overall depth divided by 2. And B we can calculate like capital B, we can calculate like small b, the bearing length, and 2 into N1. What is that N1? N1 is nothing but the distance from the top to the neutral layer. Okay, so if we can calculate the B, N1 and TW, that is also given for a specific sections, that part is also given, then we can calculate the wave buckling strength at under the concentrated load and at the support as well as. So that is nothing but the area and FCD. What is that FCD? The design compressive strength. Now the thing is how we can calculate the FCD value. FCD value, why no, we were designing that we designed that compressive member or compression members, we calculated the value, or we learn how to find out the value of FCD. Now how we can calculate the FCD value? To find out the FCD value, two things we need to know. First thing, that is what should be the effective slenderness ratio lambda, and what should be the you know yield strength of the member, and this member will comes under which buckle class. So generally we consider for the wave portion that the wave portion comes under the buckle class C. That means for calculating the FCD value, we need to consider that table number 9C of IS 800. So to have the value, or to get the value of FCD, we first need to know the lambda. So what should be the lambda value? Here the effective length, first we need to know the effective length of the wave. So what will be the effective length of the wave? That is generally taken as 0.7 time of the effective depth of the wave. That D is the effective depth of the wave. Now how we can calculate the effective depth of the wave, we will see. Now what should be the slenderness ratio? We know effective length divided by Ry. And what is the radius of gyration? Ry is nothing but root over of I by A. So it comes as 2.5 D by T. So for a idealized wave strut, the slenderness ratio is considered as 2.5 D by T, where D is the effective depth of the wave portion and T is the thickness of the wave portion. Now when we have the lambda value and Fy value, we can easily calculate the value of FCD, the design compressive strength, from table 9C. And if we know the value of FCD, we can easily calculate the wave buckling strength. Okay. Now that one is for wave buckling. Now one more phenomena can occur with the wave, that is wave crippling. Wave crippling. Wave crippling, like one of the places due to stress concentration, maybe it can occur this side, maybe it can occur on that side also. So crippling thing can occur. Now how we can calculate the crippling strength? So the crippling strength FWC can be calculated using that formula, is nothing but B2 TW Fy divided by gamma m naught. Now the thing is, for that also we need to have some load dispersion mechanism. Like in the previously what we have seen that we considered 45-degree load dispersion due to that bearing. So here also we need to consider some kind of empirical load distribution formulas. So for this, generally 1:2.5 load distribution, like the load distribution for the slope is generally taken as 1:2.5. So if that P load is acting over here, then we need to calculate the value of B1, or here we have denoted as B2, and this is your N2. Now the value of B2 will depend on B1. What is that B1? B1 is nothing but the bearing length here, B1 plus 2N2 for the concentrated load, and under the reaction this will be only N2. Okay, so under the concentrated load, that will be B2 will be B1 plus 2N2, and under the support that will be B1 plus N2, not 2N2, N2. Now N2 value, how we can calculate? Here we have considered 1:2.5 load dispersion criteria. So what should be that N2 that N2 value? N2 value will be nothing but we can calculate like 2.5 into R, that is the root radius, plus that thickness of the flange portion. So for this kind of thing where wave crippling can occur, then two things we need to know. First thing, what is my bearing length under that a particular point or under the application of load, and what is the that value of N2 due to 1 is to 2.5 load dispersion mechanism, and we will consider that. So what should be that value? How we can calculate these two values? We can easily calculate the two values using these formulas. So if we have the bearing length, like B is given as say 100 mm, say B1 is given as 100 mm. Now if that B1 is given as 100 mm, so we can calculate the N2 value. N2 value, how we can calculate? If we have some sections like ISMB 300. So for that ISMB 300, we have particular R, that root radius. We can get it from SP6. We have that particular value of thickness of flange. So when we have these values and we have the bearing length, we can easily calculate the value of N2. And when we have calculated the N2, we can directly calculate the value of B2 under the concentrated load. And if we need to calculate at the support, then we can also calculate at the support also. By this way, we can calculate the web buckling and web crippling thing. And these two things should be well within the design shear capacity. We need to ensure that thing also. So that are the general and design specifications for laterally supported beams. Now the thing is how we can design a laterally supported beams. So what should be the design steps? What should be the design steps? So first thing, the beams are subjected to lateral loading. So we need to calculate the loads. Then we need to factor them, or we need to get the design load. Then when we have the transverse loading, we can easily calculate the bending moment and shear force, the maximum bending moment and shear forces. Now when we can calculate the bending moment, or we have calculated the bending moment and shear force, then using that equation, like first we are considering that the section is plastic section. So plastic section means beta B value will become 1. So using that, ZP is equals to MDFY by gamma M naught, we can easily find out that what should be the required sectional or plastic sectional modulus for this beam. So if we calculate that ZP value, now as per the requirement from SP6, we can easily find it out which section is suitable for our design. So we will, as per that required ZP, we will go to that SP6 and we will look for different kind of, say, medium weight beam section, lightweight beam section, or different kind of heavyweight beam sections, and we select, or we need to select one specific section. Now, when we have selected the section, now we need to identify the section is plastic, compact, or semi-compact. How we can quantify or specify them or differentiate them? From table number 2. The different kind of specifications are given. Now initially we have considered the plastic section. Now we need to identify actually it is a plastic section or it comes under different kind of section, like it might be a compact section or semi-compact section, because the later on the calculation of design, bending strength, and all these things will depend on the sectional classifications. Okay, now thus in sixth step, what we'll calculate here from the table 2, you can classify your sections, whatever it is it a plastic section, is it a compact section, or a semi-compact section, using that B by TF and different kind of things. We will look into it when we will solve one example. Now in a sixth step, what we need to do, we need to calculate the design shear strength. Now how we can calculate the design shear strength? It is nothing but VD is equals to Fy by root 3 gamma m naught into your AV, and for a rolled I section, it is nothing but H into TW, right? We just have seen on 8 point what that clause is for design shear here, 8.4. So AV for a rolled section, it is nothing but H into TW. So I just have written it directly here. Yeah. So that is design shear strength. Now we have calculated the factored shear force V. We have calculated the design shear strength VD. Now we need to check whether the beam is subjected to low shear or high shear. How we can check? We need to check for two conditions. Either the factored shear force is less than 0.6 times of the design shear strength, or it is greater than. If it is less than, then we need to go for low shear and we need to calculate the value of design bending strength. So design bending strength for low shear, we can calculate using this formula. For high shear, we can calculate using this formula. Now, we have calculated the value of MD. What is that MD? This is nothing but the design bending strength of the particular section, whatever we have selected in step number 4. Now, if your that design bending capacity is more than the your factored bending moment which is generated due to the application of transverse loading, if your design capacity is more than the demand, then obviously the section is safe. You don't need to go for any trial section. Now if your that factored bending moment is more than the design bending strength, then we need to increase the size of the section and we need to you know recalculate all these things from step number 5. Okay, now we have selected the section, we have check against shear and bending. Obviously your VD also need to be greater than V, otherwise in 6th step we need to go for higher section also. Now we have calculated against that two things. One, that bending and shear. Now the lateral buckling thing, the lateral thing is not covered till now. So how we can calculate the or check for the lateral buckling things? So we will see that portion now. Let me check. The eraser is actually not working. Okay. 1 second. Let me close it and share it once again. Just wait for 1 minute. Okay, is it visible? Uh, is it visible? Confirm. Then I'll start. Okay, visible now. Just write in the chat box. One sec. Okay. Yeah. Okay. So I think now it is visible, right? Sorry for the interruption. Okay, so where we were discussing about the local buckling things, right? Okay, so now we need to check for the till now what we have ensured, we have ensured that our design is safe against shear and bending. Now we need to check against the local buckling things, right? Like we need to check for web buckling and web crippling, then deflection. So first thing, in step number 9 we will check for the deflection of the beam. Then we need to check for web buckling. Web buckling strength, how we can calculate the web buckling strength? It is nothing but we just have seen that FWB can be calculated as AB into FCD. Okay. Then lastly, we need to check for web crippling, and the web crippling strength FWC. We just have learned how to calculate the value of FWC, and the value of these two values FWB, that means wave buckling strength and wave crippling strength WC, that should be greater than the factored shear force which is induced within that beam section. So if these steps are ensured or have been ensured, then your design for laterally supported beam is done. So let's quickly go through one example here. What that example one says, that a cantilever beam of length 4.5 meter supports a dead load including the self weight 18 kilonewton meter. So what is there? So we have generally need to design a cantilever beam, okay, which is subjected to a factor load 18 kilonewton meter, and the length is 4.5 meter. Okay, the dead load is 18 kilonewton meter and the live load is given as 12 kilonewton per meter. Okay, two kind of load is applying, obviously. The bearing length is also given, the bearing length 100 mm. Design the beam. So it's a, we need to design this beam as a laterally supported beam. So first step, what I said, the first step should be the calculation of load. So what is the dead load? Dead load is 18 kilonewton meter is given. What is the live load is given? Live load is 12 kilonewton per meter is given. So what should be the total load? 18 plus 12. Now the factor of safety 1.5. So this is the total factored load which is applying on the beam, cantilever beam. So we have a basically a cantilever beam and we need to design the beam accordingly. And some load is coming, is a combination of dead load and live load. And for dead load and live load, the factor of safety as per limit state design 1.5. So this is the factored load which is applying or coming to the beam. Now due to that load, what should be the maximum bending moment and shear force? For a cantilever beam, the maximum bending moment will occur at the support. Say for example, this is A point, this is B point. So what is the value? WL square by 2, nothing but. So the maximum bending moment comes as 456 kilonewton meter. Now what is the shear force? Maximum shear force, nothing but if the length, this is the length L and this is the total load, so nothing but W into L. So that comes as this. So this is the factored bending moment which is coming to the beam, and this is factored shear force which is coming or generated on the beam due to the transverse loading. Now we need to, in second step, we need to choose a trial section. So how we can choose a trial section? First, we will consider that this section is a plastic section. So let's consider this is a plastic section. So for plastic section, the beta B value is 1. So by using that formula, Z, required is equals to M Fy by gamma M naught. So here we have find out that our required, that plastic sectional modulus is 2006.4 into 10 Q mmq. Now what we need to do next? We need to look for a suitable section whose Z is well within or more than this, not well within, more than this value. More specifically, you need to consider the value of Z while selecting the section. You need to consider the higher values of the section which have higher values of Z. So if we look into that SP6, we will find that ISLB 550 is suitable for that Z. So here for that Z, the plastic sectional modulus is 2228.16, and our requirement for plastic sectional modulus is 2006.4. So here I have selected that ISLB 550. You can go for different kind of section, but you need to ensure that whatever section you are selecting, the plastic sectional modulus should be more than the required plastic sectional modulus. Okay. Now the subsequent values like the modulus of elasticity, the overall depth, the width of the flange, thickness of the flange, root radius, all the values I have taken it from the SP6 value. Now what should be the effective depth? The effective depth is generally calculated as, overall depth or overall height of the member minus 2 into thickness of the flange eh, plus the root radius, because the root is actually not, perfectly rectangular at that portion or linear at that portion. Some curvature will be there. The root radius, here you can see that D or R, we can say here the root radius is there. So the effective depth for this wave portion, we can calculate it by this formula, H minus 2 into TF plus R, so that comes as 484 mm. So all the values we have. Now we need to define the section or identify the section, whatever it is, a plastic section, compact section or semi-compact section. So where we can get the information from the table 2. So for table 2, to use the table 2, we need to check for, BF by 2 by TF and D by TW, two values. Like if I go to that table 2 portion here, I think, yeah, the table 2 portion is there. So B by TF we need to consider, and one more thing, we need to check for D by TW value. Okay, so we have rolled section. So the rolled section, we need to check for B by TF value. Now here that comes as 6.33, and that is well within 9.4. I think 9.4 is the range for, yes, 9.4 is the range for the plastic sections. 9.4 into epsilon. Now what is that epsilon value? Epsilon is nothing but under root of 250 by Fy. Now for our case, the Fy is 250, so 9.4, and the value of, and B, what is that B? B is nothing but that BF by 2. So here from this clause we see that our section lies under the plastic section. Both the conditions, like that B by TF and D by TW, both things or both the parameters satisfies the condition of a plastic section. Okay, so we have considered is a plastic section and it turns out to be a plastic section. It's okay. Now we need to look for deflection and bending, shear. Three things are left. So first thing, we need to calculate the design shear capacity, calculation of shear capacity or design shear capacity of the beam. So calculation of, say, design shear capacity of the beam. So how we can calculate the design shear capacity of the beam? That clause 8.4 gives you the details about the design shear capacity. Now what is the design shear capacity? VD is nothing but Fy by root 3 gamma m naught into AV. That is the shear area. Now AV for a rolled section was we had seen that it is nothing but B into TW. So Fy value, put it here, calculated it, that H, total depth of the that I section, whatever we have selected. So we selected ISLB 550, so 550 will be the overall depth. TW, this is, now we have the value of the design shear capacity is turned out to be 717.47 kilonewton. Now we need to check that the section whatever we have selected, and due to the transverse loading, is the section is subjected to low shear or high shear. So how we can calculate? We just need to calculate the value of 0.6 VD. Now the value of 0.6 VD comes as 428.68 kilonewton. Now here Claude says that if the value is more than that, design factored shear force which is acting on the beam, then it is subjected to low shear. So obviously 202.5, what is that? That is nothing but the maximum shear force B, which is generated due to that load combination, dead load and live load combination. So here the section is subjected to low shear. That means we need to calculate the design bending capacity as per the low shear. That means we need to follow the clause 8.2.1. So when we have calculated the design shear capacity and identified that the beam is subjected to low shear, now we are in a position to calculate the design bending capacity of the section. So design bending capacity MD from clause 8.2.1.2. What is the value of this? This is nothing but beta B into ZP Fy by gamma m naught. Now this is a plastic section, so beta B will be 1. ZP for the ISLB 550 is that, and 250 is nothing but the yield strength. So if I calculate it, the value comes as this. Now this is a cantilever beam. This clause also says that your MD value should be well within 1.5 JD by gamma m naught for cantilever beams. So now what is the value? This 1.5 JD by gamma m naught. If we calculate that, the value is comes at 559.04 kilonewton meter. That means okay, my design bending capacity for the beam whatever I have selected, that means ISLB 550, the design bending capacity is 506.4 kilonewton meter, and this is greater than your design factored bending moment. What was the factor bending moment? 456. 456 kilonewton meter. That means okay, the section whatever I have selected for the design purpose, the section is safe against shear and also safe against your bending capacity. Now what do we need to calculate? We need to check against three more things. One is against the deflection, and we need to check against the local buckling failures. So first thing, we need to go for the deflection check. So in step 6, allowable value, right? The delta max is well within the delta allowable value. That means the section we have selected, that section is safe against the deflection limit. The safe against the deflection limit. Now we need to check for wave buckling and wave crippling. So let's quickly solve these two steps. So in step 7, we need to look for the wave buckling strength. Now how we can calculate the wave buckling strength? The wave buckling strength FWD WB can be calculated as AB into FCD. Now what is the AB value? AB is nothing but, we just have seen that AB is nothing but B1 plus N1 into TW. What is that B1? B1 is the bearing length, and the bearing length is also already given, that is 100 mm. What is N1? That is the depth from top to the neutral axis. Overall depth was 550, so it is nothing but 275 mm. Now we can calculate the value of AB. AB is nothing but that B1 plus N1 into TW. The TW thickness of that wave portion for ISLB 500 is 9.9. So 3712.5 mm square. Now we need to calculate one more thing, that is the value of FCD. AB value already calculated. Now how we can calculate the value of FCD? For the FCD we need to know the lambda value. So what is that lambda? To calculate the lambda value, we need to know the effective length and we need to know the area of this wave portion and the moment of inertia. So moment of inertia, nothing but it's a rectangular section. So B1 TW cube by 12, we can calculate it easily. So that comes as this. And what will be the area portion? Solid area portion, that is nothing but the bearing length into TW. So that comes as this 990 mm square. Now the lambda value we can easily calculate that LE by R minimum. Now the LE we have already discussed, the effective length for the wave strut is taken as 0.7 times of the effective depth, and D value we have already calculated on the previous steps. Like here, what is the effective depth for this section? That comes as 484 mm. So here we can see that the values, but the thing have gone. Yeah. So lambda value we can calculate 119. Now we have the lambda value as 119, and we have that Fy is 250. Now we can easily calculate the value of FCD. How we can calculate the value of FCD? From table number 9C. So from table number 9C, corresponding to, say, if we go to table number 9C, we can see that here table number 9C for 120 we have a value of FCD, that 83.9. So I have directly taken the value 83.9 from here. So now we can easily calculate what we can calculate, the value of wave crippling strength here, wave buckling strength, then wave crippling strength. So FCD value, the FCD value is directly comes as 83.7 Newton per mm square. Now we can calculate the FWD value, and FWD value will be nothing but the value of AB. So the value of AB is 83.7, and the value of FCD we have, the value of AB is 3712.5, and the value of FCD we have just calculated from table number 9C, and that comes as 83.7. 83.7. Okay. So now what we have seen here in this step, that the wave buckling strength comes as 310.7 kilonewton. And what was our criteria to safe against the wave buckling strength? That your wave buckling strength, if WB should be greater than your factored shear force which is induced on the member. So yes, we can say now that that section we have selected as a lateral unsupported beam, the section is safe against your wave buckling. Now we need to look for the one more thing, that is wave crippling. So how we can look into the wave crippling thing? So we have the formula for wave crippling, like here we have already discussed earlier. Still we will solve this. Yeah. So check for wave crippling. Now how we can calculate the wave crippling strength? Wave crippling strength can be calculated using FCW. FCW is equals to B2 TWFY by gamma m naught, and where B2 is nothing but the bearing length plus N2. Now this N2 is calculated with respect to that empirical load distribution formula. That is it visible to everyone, or just missed it? Yeah. So is it visible? Actually, I am facing that internet issue here today. Yes. So now one more steps is left, that is check for wave crippling. Now how we can calculate the wave crippling thing? We can easily calculate the wave crippling strength using the formula FWC. is equals to B2 into TW Fy by gamma m naught. That what is B2? We can calculate it using the bearing length whatever is given, and N2 we can calculate it using the empirical load distribution whatever we have considered previously, like 1 is to 2.5, this value. So N2 we can calculate like 2.5 R plus TF. R for the ISLB ISLB 550 is 18 plus TF value is 15, so this come as 82.5. Now we can calculate the FWC value, B1 plus N2 TW into F by gamma m naught, and if we put all these values here in this equation, we can see that the design or the web crippling strength come as 410.6 kilonewton, and which is greater than the factored shear force which is generated on the beam section. So we can say, okay, now this section is safe against web buckling and web crippling both. So let's quickly summarize the thing what we have covered during the design of laterally supported beam. So first what we have did, we calculate or we have selected. So first thing, let me remove the picture from here. Okay, so first thing, what was given in the question, we need to design a cantilever beam which is subjected to a combination of dead load and live load. So for this thing what we have done, that we just calculate the factored load, and due to the factored load in step 2 we have calculated the maximum bending moment and maximum shear force. Then in step 3 we have calculated the required sectional modulus, whatever the sectional modulus is required with respect to that moment or the total factored bending moment. Then we got the information, or we have selected one section like with respect to the required plastic sectional modulus, the ISLB 550 is the suitable section for this, and for the ISLB 550 we have taken all the values from SP6. Then on the next stage what we have what we have done, that we have classified the section, whatever the section is plastic, semi compact or compact, because on the initially to calculate the value of Z required here on this step we have you know assumed that the my section is a plastic section. Otherwise we need to calculate the we had to calculate the beta v value. Now then what we have calculated, we calculated the design shear capacity, and then we checked the section is under high shear or low shear. Then we go for that design bending capacity, and here for the problem we have seen that the beam is under low shear. So as per the clause 8.2.1.2 we have calculated the value of the design bending strength, and for the cantilever beam we have checked the condition for that to avoid the irreversible deformation under serviceable condition, that is while within that condition. Then we go for the wave buckling and wave crippling strength. So in the step 6 we have calculated the value of deflection. Then in step 7 we calculated the wave buckling. So the beam is check against wave buckling. Now once the wave buckling strength we have calculated here, that wave buckling strength and wave crippling strength, both strength are well within or more than the design shear capacity. So now we can say, okay, the beam is safe against deflection, bending, and against the local buckling things. Okay, so now we will move to another kind of beam, that is laterally unsupported beams. So till now, do you have any questions? Okay. Okay, now we will spend some time on laterally unsupported beam. Like in laterally supported beam, what we have seen that the beam is supported on the lateral directions, but here the lateral supports are not provided. Okay, so the clause 8.2.2 deals with the laterally unsupported beams. Okay, now what this clause says, if we have a laterally unsupported beam, then for this case the design bending stress can be calculated as MD is equals to beta B ZP into FBD. Now, how we can calculate the FBD value? Here we can see that what is that FBD? That is nothing but design bending compressive strength. Either we can obtain from table 13A or 13B based on the condition, or we can calculate the value using that FBD is equals to zeta LT into Fy by gamma m naught. Now this will vary for different beams. Like for simply supported beam, we can have the xi LT value, or more specifically, we can calculate the value of zeta LT using that formula 1 by phi LT plus phi LT square minus lambda LT to the power half, and this value is always less than 1. Now the thing is that phi LT, how we can calculate the phi LT value? The phi LT value can be calculated as 0.5 under bracket 1 plus alpha LT. The value of alpha LT is 2.21 for rolled section and 0.49 for welded section. So if we can calculate phi LT, we can calculate zeta LT value, and subsequently we can calculate the value of MD, that is design bending strength for laterally unsupported beam, and that is nothing but beta B. What is that beta B? That is a factor which deals with the sectional properties. Like if it is a plastic and compact section, the value will be 1, and otherwise for semi-compact section we need to look for the ratio of elastic and plastic sectional modulus. Okay, beta B ZP FBD. Okay, so let's quickly solve one more example so that these concepts will get more clear, right? Okay, so here we can see that different kind of MCR value we can calculate. Like here, to calculate the value of the lambda LT value, you need to calculate the value of MCR. The MCR value, what is that MCR value? It is nothing but elastic critical moment. Now, how we can calculate this? We can calculate using that formula 8.2.1. So here the formula is given M shear, we can calculate using this formula. So this to calculate the design bending strength of laterally unsupported beam, either we can follow these formulas or we can directly get the values from the table. Okay, so let's quickly solve one example, then we will move to the assignments portion. Okay, so here calculate the design bending strength of ISLB 300. Now, for two conditions, we need to calculate the design bending strength for laterally supported case and for laterally unsupported case. And this is a simply supported beam, and the effective length is also given as 4 meter. Okay, assume the grade 410, and also says that you need to design for low shear. So the relevant properties of ISLB 300 we can get from SP6 1, where the D is the overall depth, BF width of the flange, TW thickness of the web, TF thickness of the flange, and the IZ and IY the modulus of elasticities, and the D effective depth we can calculate by overall depth minus 2 into TF plus R1, just we have seen. In the second step, we need to identify what kind of section is this. So we need to look for table 2. First thing, we go for BF by 2 divided by TF, that value well within 9.4, and dy TW, that check is under that plastic section conditions in table number 2. Just we have seen in when we just calculate the design strength of laterally supported beams. So the section is plastic section. Now accordingly we need to calculate the design bending strength for plastic section. So for first thing, for laterally supported beams, clause 8.2.1.2, and the section is plastic. Secondly, for low shear, the question is given that you need to calculate the values for the considering the low shear condition. Now put all these values, you can find out the value of design bending strength. And beta b for that section is a plastic section, so beta b is 1. Zp for that section is given already, or we have taken it from sp6. Now fy value, put all these values, that comes as 125.98 kilonewton. Now check, this is a simply supported beam, so we need to check against irreversible deformation under serviceable loads. So that comes as 133.34 kilonewton. So what should be the value of design bending strength? Minimum of these two values, 125.98 kilonewton meter and 133.34 kilonewton meter. Now for the laterally unsupported case, we need to calculate it. So first thing, for the laterally unsupported case, we need to calculate the M shear value. So what is the M shear value? We can get the equation from clause. So M shear value, to calculate M shear value, we need to know the effective length, that is already given. We can calculate the G value considering the mu is equals to 0.3. So that comes as 76.92 into 10 cube. Now torsional constant IC, this formula is also given on your code, that summation of BI/TI cube by 3. So 2 into this formula, comes as this. Now warping constant IW, that is also given in your code, that comes as this. So using that values, if we put on the equation, then phi LT comes as 1.35. Now corresponding to that phi LT, we need to calculate that xi LT value. So xi LT comes as 0.52, and this is well within your one limit. Now when we have the value of xi LT, so now we can calculate the FBD value. FBD is nothing but xi LT Fy by gamma m naught. That comes as 118.2. Now when all the values are provided, now we can calculate the value of MD as beta B multiplied by what was the formula for that? Beta B ZP into FBD. So ZP, we have the value of ZP into FBD. FBD value we have just calculated. Now put all these values. The value comes as 65.52 kilonewton meter. It's a moment, so kilonewton meter. Now this is the process using the formulas. Now if we use the table, right? Table 14 and table 13a. We just need these two tables. Like for corresponding to that FY 250 and the KLRY value, this we can directly calculate the FCRB value from table number 14. Like the table number 14 is given here, FCR into B value with respect to lambda and with respect to H by TF value. So with respect to lambda and with respect to H by TF value, you can easily get the value of FCRB. And when you have the value of FCRB, using the equation, you can calculate and that equation, this equation, we have the equation given in your code. So the values are similar. You can see that if I use the table, the value comes as 155 Newton per mm square, and if I use the formula given on your code, then that comes as 153. Now, when we have that FCRB value, FY value, and alpha LT value, we can easily calculate the value of FBD, the design strength, from table number 13A. Here you can see from table number 13A corresponding to FCRB and FY, we can calculate the direct value. And for alpha LT, for two alpha LTs are given, like 13A and 13B, two tables are given. So that corresponding to that value, we can easily calculate the value of FBD. Okay. Now, if we put all these values, that comes as 60.71 kilonewton. So if we follow the tables directly, then the MD value comes as 60.71 kilonewton meter. Now, if we follow the formula, the MD value comes as 65.52 kilonewton meter. More or less similar. But for the design purpose, either we can go for the that tabular form, or we can go with the equations one. So that's all for the beams. Now we will solve the examples. So do you have any doubt or queries? You can ask me, or else we can start solving the previous year questions. Okay. So what the first question says, question number 1, what is the effective length of a beam if compression flange is partially restrained against lateral bending and partially free to rotate in plane? So from where we get the information? In table number 15. So if we look for the table number 15, we can get it the value partially free to rotate in plane. So that is 0.85, or you can take it the value from here also, 0.85. Compression flange is partially restrained. So the option number C is the correct option. Now, question number 2. What is the effective depth of the wave in case of buckling if it is restrained against rotation but not against lateral deflection? So it is nothing but D1, the depth of the wave portion. Now, question number 3 says design bending strength of a simply supported beam should not be less than. If you visit the clause 8.2.1.2, you can see that for low shear case, the design bending strength can be calculated as this formula, and this is checked for if this is simply supported beam, the value should be less than 1.2 JDFY by gamma m naught. And for cantilever beams, the value is 1.5 JDFY by gamma m naught. That means that for simply supported beams, the value is that. That means for simply supported beam, if you need to calculate the value of MD, that MD should be equals to minimum of your, that formula gives you ZPFY by gamma m naught and 1.2 ZE gamma m naught. Okay. So option B is the right answer. If for a cantilever beam, then that will be 1.5 JDFY by gamma m naught. Now, question number 4 says a cantilever beam supports a dead load of 15 kilonewton per meter and a live load of 12 kilonewton per meter. The length of the beam is given 3.5 meter. Which of the following section is the most suitable section for the trial section? Okay. So we need to calculate ZP required. That will be equals to nothing but M into gamma m naught by Fy. Right? We have calculated using that formula here. Here. Okay. So the formula here written is like Z required will be m into gamma m naught by Fy. So please make it correct. That should be equals to m into gamma m naught by Fy. That means that will be equals to nothing but 456 into 10 cube divided by 250 into 1.1. Now if you calculate it, so it will comes as 256 into 10 cube into 1.1 divided by 250. Yes, that comes as okay for this value. So please correct this equation. Okay, this part. This will be equals to m into gamma m naught by Fy. So let's move to our question. Here. So first we need to calculate the total load. So total load will be 40.5 kilonewton, and is the are factored load. So I think these are not factored load. So the factored is given here. So total load will be equals to total factored load. This is nothing but the total factored load. Total factored load. Okay. Now we can calculate the bending moment. It is a simply suppose this is a cantilever beam. So bending moment WL square by 2, that comes as 248.6. Now we need to select the section. So we need to calculate the ZP required. So ZP required will be equals to M into Fy by M into gamma m naught by Fy. Gamma m naught by Fy. Because our MD was equals to the value of beta B ZP divided by gamma m naught. So eventually ZP will become M into gamma m naught divided by Fy. Okay. So that comes as this. Now we need to go to that SP6 and look for that out of these four sections whose sectional modulus or plastic sectional modulus is near about that 1091.5 into 10 cube mm cube. So here we have seen that ISHB 350 have the sectional modulus 1213.53, that is close to 1091.5. That means the option number A will be the correct answer. Now move to next question. A simply supported beam of span 4 meter is laterally supported throughout and carries a uniformly distributed load 42 kilonewton, including its self weight. 42 kilonewton. Okay, the total load. Now the thing is that is for okay to get the total load we just multiply with the length. Okay, the beam comprises ISLB 250, and for the ISLB 250 the values are provided. So you need to calculate the value of maximum deflection first. Okay, calculate the flexural strength and maximum deflection due to load. Two things you need to calculate here. First thing, You need to calculate the maximum deflection and you need to calculate the bending strength. Okay, here two things are given, that assume the section is plastic and take the Young's modulus as 2.5 into 10 to the power 5. So what we need to calculate? First we need to calculate the factor bending moment, then we can calculate the bending strength, and subsequently we can calculate the deflection. So what will be the value for that? So factor load, the factor load will be 1.5 into 42, that means 63 kilonewton. Now what will be the factor bending moment? The factor bending moment will be M will be W into L square by 8. So total load W into L is given, the total load is given. Okay, this is the total load is given. So WL is given into L by 8. So if you put all these values, then 63 is the total factored load multiplied by 4 meter is the length of the beam divided by 8. That comes as 31.5 kilonewton meter. Now, this section is a plastic section. That means the beta B value will be 1. Now, so what will be the value of design bending strength MD? MD will be equals to beta B into ZP for this section multiplied by Fy by gamma M naught. So if we put the values, ZP value is provided here. Fy value 250 is given. What is the value of gamma M naught? The gamma M naught value is 1.1. So if you calculate this, this value comes as 76.9 kilonewton meter. So here Newton millimeter is given. So 79.6 is 76.9 kilonewton meter. Now this is a simply supported beam. Now for simply supported beam, we need to check for one condition also. That is 1.2 JDFY by gamma M naught. So this value is coming at 76.9. That is also coming as 76.9. Now, so what will be the value of MD? Obviously 76.9. So we have 76.9 answer. Now we need to check for one thing, that is the deflection. So for a simply supported beam subjected to deflection, the subjected to uniformly distributed load. So what will be the maximum deflection value? The maximum deflection value delta max will be equals to nothing but 5 by 384 into 5 by 384 into WL to the power 4 by EI. Now, if you plug in all these values here, the deflection value comes as 7.06 mm. That means the option A is the correct answer for this question. Okay. Now move to next question. The maximum deflection in beam. So here the uniformly varying load is provided. So that the maximum deflection value del for this kind of loading arrangement, delta max is coming as 7 W L cube by 1920 EL. Okay. That means your option D is the correct answer. Now, the bending stress reduction factor, okay, this is given on your clause that the value is like 1 by phi LT plus under root of phi LT square minus lambda LT square. Now, question number 8. What is the web buckling strength? We need to calculate the web buckling strength of ISMB 300 is given. Okay, assume the bearing width is given also 100 mm. Width of the flange is given 140 mm. Thickness of the flange is given 12.4 mm. Thickness of the web and root radius all are given. Now we need to check the web buckling strength. Okay, so web buckling strength, how we can calculate the web buckling strength? So first thing we need to calculate the value of AB. AB is nothing but, because the web buckling strength, if say WB is nothing but your AB value, you need to calculate the value of AB multiplied by the value of FCD, because the web will act like a column. So AB value how we can calculate the value of AB, the area. So the AB value is calculated as B1, the bearing length, whatever is provided, plus N1, that is the distance from top to neutral axis, multiplied by TW. So what is the value of B1 provided here? The B1 is given as 100. What is the value of N1 will be? The total depth is 300. So 300 divided by 2 multiplied by TW. What is the value of TW given here? 7, I think 7.5. So this is the value of AB. So if you calculate the value of AB, that comes as 1875 mm square. Now, what should be the effective length of the wave? Because we need to calculate the FCD value. So to calculate the FCD value, we need to know the lambda value. So how we can calculate the lambda value? Lambda for a, we just have seen the lambda for a that wave portion. We need to calculate like effective length by R minimum. Now, what will be the effective length for this case? We have seen that we need to consider 0.7 times of D. D is the effective length, effective width, effective depth of the wave portion. Now, how we can calculate the D value? D value is calculated as capital D minus 2 into that value of your TF plus R. So the all the values we have taken it or the given here. Okay. Yeah. So that comes as 247.2 mm. Now we need to calculate the I value. I is nothing but B TW cube by 12. So B, that means the bearing length is given as 100 mm, 100 into 7.5 cube by 12. So that comes as 3515.625 mm cube. Now that is the, what is the area of the wave portion? Area of the wave portion will be B into TW. So that comes as 750. Now we can calculate the R minimum value. R minimum will nothing but root over of I upon A. So I value comes as 3515.625 divided by 750. So that comes as 2.165 mm. Now we can calculate the lambda value. Lambda is nothing but L effective by R minimum. That comes as 79.92, nearly 80. Now for the 80, you need to look for table 9C, where you can find the value of FCD. So table 9C is not here. But if you look for the table 9C, the allowable stress will come as 136. So let's go to that table 9C once again. I think I have table 9C added here. Yeah. Here you can see table 9C as per lambda value 80. You can calculate the value of FCD 136. Now we can calculate the wave buckling strength. So FWB is nothing but AB value we have calculated is like 1857 multiplied by the value of FCD. So the value comes as 255 kilonewton. So 255 kilonewton, answer will be the right answer. So 255 kilonewton. First thing, what we need to calculate? AB value. Then we need to calculate the lambda value. Then corresponding to that lambda value, we need to calculate FCD value. When we have AB and FCD value, we can calculate the wave buckling strength. FWB is equals to nothing but AB multiplied by FCD. Okay. Now move to next question. Now, what is the wave crippling strength at support for the above question? Okay, at the support, wave crippling strength at the support. So what is the formula for wave crippling strength? FWC will be nothing but B1 plus N2. Now for the support it will be N2, for the under the load it will be 2N2 into TW into Fy divided by gamma m naught. Now we have the value of B1, that is the bearing length. B1 is given as 100 mm. Assume the bearing width is given as 100 mm. Now how can calculate the value of N2? N2 we can calculate as per our corresponding to the load distribution 1:2.5. We can calculate it. So from this formula 2.5 into R plus TF. The value of TF is given on the previous question. So N2, if we plug all this equation, N2 comes as 66 mm. Now plug all these values here. So 100 plus N2 is 66, multiplied the value of TF is given as 7.5, okay, multiplied by TW, the value of TW, thickness of web, multiplied by 250 divided by 1.1. If you solve it, you will find the value is 282.95 into 10 to the power 6 Newton m, 10 to the power 3, I think 3 Newton. Now 282.95 kilonewton. So this will be the right answer. Now one more question is left. So let's quickly solve the question. What the question says? A laterally supported beam is carrying maximum shear force 120 kilonewton. Okay, the shear force is given, maximum shear force V is equals to 120 kilonewton. Now the maximum flexural moment is given also 80 kilonewton meter. The span of the beam is length is given as 5.2. Find the design shear strength of ICLB 300 whose thickness of the flange is given, thickness of the wave is given. So how we can calculate the value of VD, design shear capacity or design shear strength, is nothing but Fy by root 3 into gamma m naught multiplied by the area H or D, total effective total depth into TW. So if you plug in all these values like 250 divided by root 3 into 1.1 multiplied by H for ISLB 300 is 300 plus TW. What is the value of TW? Thickness of wave thickness 6.7. 300 into 6.7. That Newton. So that comes as 263.74 kilonewton. So 263.74 kilonewton will be the right answer. Okay. So that's all for today. So if you have any questions, you can ask me, or else we can conclude the meeting here and we will meet on the next class. So generally what we have done, first thing in today's class, we have learned about beams. Then we learned about laterally supported beams, how we can calculate the design bending strength, how to design them, all these things. And thirdly, we have seen the laterally unsupported beam. Okay. So for now, if you don't have any questions, then we can conclude here. We will meet on the next class. Thank you.